All right, welcome to The Explainer. Today we're diving into a really beautiful story, a new solution to a problem that's centuries old. It's about a 5-year quest that uncovers this hidden geometric link between, the regular old whole numbers and one of the most famous numbers in all of math, pi. So let's just kick things off with a real head-scratcher, one that stumped the greatest mathematicians for the better part of a century. We all know pi, right? It's all about circles. So what in the world is it doing showing up in an infinite sum of fractions? I mean, a sum that looks like it has absolutely nothing to do with circles at all. Well, this thing has a name. It's the famous Basel Problem, and it's asking a pretty simple question. What is the exact value you get if you add up the reciprocals of all the perfect squares forever? For like 90 years, mathematicians knew the answer was somewhere around 1.64, but nobody, and I mean nobody, could pin down exactly what it was. That is, until the absolute genius Leonhard Euler shows up in 1734. He made this unbelievable connection between the sum and the sine wave, which, is all about circles and waves. His solution was a total landmark, a real game changer. But, as we're about to see, it wasn't the only way to crack this nut. Okay, so now let's fast forward almost 300 years. We're going to jump to a much more recent and way more personal journey. A 5-year quest to find a completely new solution, one that looks at the entire problem in a new light, not with algebra, but with pure geometry. And this right here is where our story really begins. This quote just speaks to an incredible level of dedication, right? A single person wrestling with this classic beast of a problem, just determined to find an angle that no one had ever seen before. This was never just about getting the right answer. It was about discovering a whole new path to get there. So what was the big idea, the key that unlocked it all after 5 years? Well, believe it or not, it wasn't some complicated new equation. It was a picture. Okay, so instead of just adding up a boring list of fractions, this new approach does something kind of radical. It says, let's visualize every whole number, 1, 2, 3, and so on, as a point in space. Now, imagine each of those points has a little bit of influence, kind of like a tiny electric charge. And here's the kicker. You don't just place them randomly. You arrange them on this incredibly specific and really beautiful curve, a logarithmic spiral. And here it is. Just look at that. Isn't that beautiful? You can see each point, n equals 1, n equals 2, n equals 3, finding its own special spot on this curve. All of a sudden, the problem has been transformed. We've gone from a flat, one-dimensional sum to this gorgeous two-dimensional shape. The secret, it turns out, wasn't in the numbers themselves, but in the incredible shape they make together. So the big question is, how do we get from this pretty picture to an actual answer? Well, the trick is to stop looking at the individual points and start looking at what they do as a group. Now, the key to this whole thing is a little parameter we can call epsilon. Just think of it like a dial or a knob you can turn. When epsilon is bigger, the spiral is kind of loose. But when you dial epsilon way, way down, the spiral winds itself up incredibly tightly. And this is where the magic happens. As you turn that epsilon knob closer and closer and closer to 0, these individual points on the spiral get packed in so tight that they start to lose their identity. They literally start to melt together. This whole process, this transformation, actually has a name. It's called taking the continuum limit. What you're seeing is the collection of separate individual points on the left, transforming into the perfectly smooth continuous ring on the right. An absolutely perfect circular symmetry just emerges from what looked like a bunch of disconnected points. The spiral literally melts into a circle. Okay, so we've got a circle. Now what? Well, this is where that beautiful new symmetry basically just hands us the answer on a silver platter. Because in this limit, when you calculate the combined influence, that total charge from this new continuous ring of points right at its very center, what do you get? You get this. Pi squared over 6. Exactly. Not an approximation, not an estimate. It is the precise value that the geometry itself demands. So you might be thinking, okay, a circle means pi, I get that, but why is it pi times squared? Well, it's because two different parts of the geometry each chip in. First, when you sum up the influence around the circle, that perfect rotational symmetry naturally spits out a factor of 2 pi. Then, when you do a second calculation, this time moving from the center outwards along the radius, you get the other pieces you need to build the final answer. It's really incredible. And you don't just have to take my word for it. The math totally backs this up. Look at this table. It shows the calculated sum for different values of that winding knob, epsilon. See what happens? As epsilon gets smaller, as we tighten that spiral, our calculated answer just zooms in, closer and closer, right onto the real value of about 1.6449. It's like it's homing in on a target. So, what's the big takeaway here? What does this whole new proof really teach us about this deep, deep connection between numbers and shapes? Well, what we have now are two totally different but equally amazing ways of getting to the same truth. Euler's proof was this masterpiece of algebra, like a symbolic dance. This new proof, well, it's a masterpiece of geometry and physics. It doesn't rely on algebraic tricks, it relies on the physical symmetry that just pops out of the numbers themselves. It's about seeing the answer, not just calculating it. I love this quote because it just nails it. The answer, pi squared over 6, isn't just some weird, quirky result from an equation anymore. In this new light, it's a geometric inevitability. It means the answer had to be this, because of the shape. The circle was always there, just hiding inside the numbers, and this is its signature. And that just leaves you with this incredible final thought, right? This 5-year quest didn't just solve an old problem again, it showed us that the integers, the simple counting numbers, seem to hold the blueprint for a perfect circle. And that just makes you wonder, if a circle is hiding in there, what else is hiding in our number system? What other beautiful hidden geometries are just lying there waiting for someone to find the right way to look at them?